Okay, uh, folks, at the risk of jumping the gun here and starting 30 seconds early, I think we'll maybe just do that. I want to take a quick look at the participant box here and maybe get a little idea. I'm guessing most people on the program today are probably from New England, probably a group of architects and engineers. And I'd like to say welcome, happy holidays, whatever might apply to your own set of beliefs. My name's Roger. I'm down in Highland Beach, Florida right now. And okay, I see another person just joined. So let's establish a few ground rules here. With 21 participants, it's kind of hard to have open mic. So what we'll do is I'm going to ask you to please, if you have comments, and I want this to be as interactive as possible, please use the Q&A box for questions and answers. That way I can keep track of the questions that I've answered. And don't be afraid to ask questions. That's what you paid top dollar for today, is to be able to have a discussion. And you know, the worst question you would ask would be not asking any. Worst case answer would be, we're going to cover that a little bit later. So let's get started. Let's see, I did unmute, didn't I? Yeah, that's a good thing to check to begin with. Okay, here we go. From this first slide here, you'll notice it's a sunrise. And in fact, the sun's been doing that for about the last 4.5 billion years. And it's probably going to keep on doing that for another 4.5 billion, at which point we've got about 8.5 minutes to figure out a new energy source. But for the moment, it should do pretty well. It's pretty predictable when it's going to rise, when it's going to set. And we've got some pretty good ideas on what to do for those times when it's not shining so brightly. So we're going to look at just basic photovoltaic systems today. And using the following outline, we're going to talk about which kind of system might you want to install. Then we're going to do some structural things. And then we're going to do the electrical design considerations. Then we're going to look at how do you estimate the performance of the system, at which point it will be time for lunch. We're going to go through this in a fair amount of detail, including down to wire sizing and so forth. So, and fact of the matter is, what we're going to show today are very basic principles of the design. And it's important to understand these basic principles because the whole design process is changing very quickly. The kinds of equipment that are available, meeting the new code requirements and installation requirements, things change. But from what I've seen over the last 20 years, they are changing very much for the better. You look at the 2020 National Electrical Code requirements for photovoltaic system design, much more concise, much more understandable, much more comprehensive than those in the 17, 14, 11, and the other previous editions. So things are doing fine here. And fact of the matter is, a friend of mine who's in the PV, his PE business is strictly limited to design of photovoltaic sources, and he is looking for people. There aren't that many engineers who are good at it. So if you're looking for some extra work, and maybe you're all busy as you can be, certainly PV design is going to be wide open here in the next 15 years or so. So let's move on with that background material. Let's take a look at selecting a system. There will be some times here where I'll go kind of quickly because it's just information that I want you to know that is in the content of this presentation. And it'll be things that you can come back to for gory details, like some formulas and so forth, if you order up the set of PDF slides after the program is over with. So let's first talk about the sun. It helps to know a little bit about it. At ground level, if the sun is directly overhead, the peak sun intensity is 1,000 watts per square meter. And I see we have a question. Let's take a look and see what that might be. Where do you get the PDF slides? After the program is over, you'll be able to download a set of slides, and the host will be putting the answer to that question in the chat box. So the slides will be available after the program is over. And let's see, I answered that one live, so I'm going to click done on that. And okay, and that's the way we hope to get through questions and things. I hope that I will catch it at the top of my screen so that we won't miss anything. Okay, so the sun peak intensity is 1,000 watts per square meter. This is measured in units that are very useful for electricity, watts, you know, square meters. That helps a lot to know how many square meters you've got on a roof. Okay, about 20% of this, depending on which technology you're talking about 20% of that can be converted to electricity with photovoltaic technology. All right, and annual conversion range, see, it turns out you're not collecting 1,000 watts per square meter every hour of the day that the sun is shining. Yeah, mostly you're collecting less than that, and for reasons that will become evident as we move through the program here. So the more reliable thing to look at is what's your monthly collection expectation for a particular system size and orientation and so forth, or what's your annual conversion expectation. And so we're going to measure that in kilowatt hours per kilowatt per year. In other words, if you install a kilowatt of photovoltaics, then how many kilowatt hours per year can you expect it to provide for you? And in general, around the country and around the world, it's somewhere between 1,000 and 2,000. If you're out in the middle of the Mojave Desert, you might get 2,200. But a pretty reasonable average number to use for estimating purposes is about 1,500 kilowatt hours per kilowatt per year. So if I put in a 1,000 watt photovoltaic system, I can expect it probably, if it's facing south, in a reasonable location to generate about 1,500 kilowatt hours per year. Now, there are very sophisticated computer performance models that are available that you can take a look at the proposed site on a Google Earth or other mapping device that shows the proposed site. You can get a pretty good idea of orientations, tilts, and lots of other information. You'll know the location. The performance models take into account weather, cloud cover, all kinds of different things, annual models, and give amazingly useful predictions on a monthly basis. Of course, on a daily basis, that's another story. You don't necessarily get good daily provisions because it's really hard to predict when it's going to rain next year exactly. So anyway, what are the types of photovoltaic systems out there that we might consider purchasing or designing? Well, there's the standalone system, and I put this one in on purpose to show that photovoltaics really does work in Alaska. This is on the Kenai Peninsula and the entrance to the exit glacier. Well, yeah, if you're coming up. If you're going downhill, it's the exit to the exit glacier. And but it's a nice standalone system where they get enough power to run whatever they need in that entrance station. And then there's grid connected systems. And if anybody of you live up in the neighborhood of Tupper Lake, New York, this is at the Nature Center in Tupper Lake. And this was there a long time ago. And it's one of the more neater systems that it's almost as though the roof was designed exactly for this PV system. And this is a straight grid interactive system here. There's more than just straight grid interactive, but basically we're either all by themselves off the grid or we're going to connect to the grid with whatever we design. And so we'll look at some more options. Here's a few examples of off-grid systems out in Nevada, Wyoming, Utah. And North Carolina, you can get decorative if you want. There's not a whole lot of electricity generated by that tree there, but it illustrates a point. You can go up the Yellowknife in the Canadian Northwest Territories, and you'll find all kinds of interesting ways of generating electricity, wind, solar. You can go to North Branch, Minnesota, where Xcel Energy has got a 100 megawatt photovoltaic system using these huge 1.5 megawatt inverters that you see in the lower right-hand corner. So there's pretty wide range. We're talking about 100 megawatts up there in the upper right, and probably about, that's probably about 3, 4, 5, 6, 7, 8, 9, 10, 11, probably about 1,200 or maybe 1,500 to 2,000 watts up there on that tree. There's a lot of PV up in the Northeast, Massachusetts. There's some in Florida. Not as much as we'd like. We got room for a whole lot more, but it's growing fast. Utilities are building a lot of megawatts of PV here in Florida because it's their cheapest way to make electricity now. And there's a little over 100 schools around the state that have 10,000 watt battery backup school shelter systems. So, and Urban Solar, a company I've had an association with, had the contract to do that work. So battery backup is something that actually the first system I designed was battery backup. And another picture in Yellow Life, just because it's kind of fun to take pictures of these PV systems. So let's talk about some of the options for grid-connected systems. One of them is just straight grid connect. They make electricity when the sun shines and the grid is operating. If the grid goes down during the day when the sun is shining, the PV system has to go down as well, because otherwise, let's say the grid goes down because there's a wire broken or something like that, and they need to get a utility crew out there. Utility crew does not appreciate backfeed electricity from a photovoltaic system when they expect that line to be dead. So the inverters have to be sensitive to whether the grid is operational or not. And we'll talk a little more rules there. That's UL 1741. And the nice thing about grid-connected photovoltaic systems is that if they're making more electricity than is needed by the occupancy, the remainder gets sold back to the grid, and typically at the same rate at which the owner is paying utility for the electricity, which is still generally a pretty good deal for the utility, because when this PV electricity is being made during peak time for the utility, generally it costs the utility a whole lot more to make electricity during their peaking time than what they would end up buying it back from a owner of a photovoltaic system. So that's a straight grid connect, no storage, no backup, and if the grid goes down, the system goes down. Now, there's always an exception. IEEE 1547-2000 now provides for an agreement to be signed with the utility that the utility can keep your system running, because a PV system can actually help the utility in the afternoon by generating electricity when the utility needs it the most. And if the utility is getting overloaded to the extent that their frequency drops where your system might go off, that would actually exacerbate the system. So the utility would like to be able to keep the system up as long as their grid is intact. So that's just a new change as of this year. They've been talking about it for a while, but it went into effect this year. Okay, and then there's the battery backup grid connect, and it has all the features of the straight grid connect system, but it also has separate standby circuits that are powered by photovoltaics and by batteries when the grid is down. And the batteries can be charged either by the utility or by the photovoltaic system. If the grid is down, then you depend on the sun to charge the batteries. We are going to focus mostly on straight grid connect. Battery backup systems are basically a 2-hour webinar in themselves, which is also available through PDH. So if you just decide you really love this stuff by the time we're done today, I'm not sure when the battery backup comes up again, but it's one that we developed at the request of people who took the straight grid connect. And there's a lot to battery backup, including now incorporating the Tesla Powerwall and so forth as the battery backup system. So it takes a whole 2 hours just to do a battery backup. Okay, so how do you decide what you want? Well, do you want to make 5,000 kilowatt hours a year? Do you want to make half of the electricity you use with the sun? Do you want a standby source that'll be there if the grid goes down? Do you want to add as much to the grid as you possibly can? Do you want to fill up your roof completely? Do you want to make sure your refrigerator runs if you have an outage or a few other loads? Or do you want to run off grid? I mean, these are some of the possible options here. You'll have to decide standalone or grid connected. If you have a grid, you're going to want to go grid connected because that way you use all of your electricity. Whatever you don't use goes back to the grid. See, a question popped here. Let's see what we got. I didn't catch the name of the regulation that was cited as recently changed. Okay. Thank you for asking that. That is IEEE 1547, which is the regulation for any kind of inverter, whether it's for photovoltaics, for wind, or even the inverter that's in a power wall. Any inverter that is connected to the utility is regulated by IEEE 1547, and that standard was amended in 2020. Okay. Okay, close that. That's it for Q's and A's for the moment. And I really appreciate seeing that Q&A box light up because it tells me at least one person's awake out there. And I'm hoping that we'll present material that is worth staying awake for. So the next question is, are we going to go standalone or grid connected? The answer there pretty much is if there's a grid in general, you want to connect to that grid. Some people want to get off the grid, but in a way, if you can sell back to the grid, why waste that extra electricity if you have it? So that's my opinion to the answering of that. There, I know this is spirit of independence and all that, but why not share some of that extra electricity so somebody else can use it? After all, you're getting paid for it. You want batteries or not? Is there a budget constraint? At this point, when we talk about budget constraints, I just want to let you know that photovoltaic electricity is now, for the utilities, the least expensive electricity they can generate. Some of the utilities are generating electricity at less than 3 cents a kilowatt hour with the sun. And for a typical residential installation, right now that may run in somewhere around $3 a watt, but then you get a right now until the end of the year, it's a 26% investment tax credit on it. So that's basically a 26% direct discount. You're making essentially 6-cent electricity. So if that's replacing 15-cent electricity, that means every kilowatt hour you're making, you're using 6 cents to pay for the system, and 9 cents is profit. And that's not a bad investment. And that's partly why so many PV systems are going in these days, and especially up in the New England area. I think Massachusetts, I think, is one of the leading states in per capita installation of PV systems. So anyway, you need to know that up front, that PV is extremely cost effective now, and there's almost no reason why somebody shouldn't have it unless the location they're planning to install it is totally shaded. What we're finding here in Florida is that it is now even cost effective to put photovoltaic on a north-facing roof as long as the slope is not too high. And that's never been the case before. But even on a north-facing roof where you maybe only get about half as much sunshine, and then for those modules, you're getting 12-cent electricity instead of 6-cent electricity, which still puts you ahead of the curve. So I didn't realize, well, it's 2 weeks ago, this first time I saw a system with some north-facing modules, and I looked at the financial analysis, and the payback was good. So very interesting. Things that we never would have imagined 10, 15, 20 years ago in this business. And now they're happening. So it's pretty exciting for an old guy like me. I mean, I'm 77 years old, and only recently started working for a former student, evaluating and reviewing sets of plans for him because he's looking for people. He had settled for the old guy. But anyway, it's been a real joy to do that because I'm learning a whole lot. And it's always nice for an old professor to learn from his former students. All right, enough of that. So what about some more criteria? Do you have any space constraints? Constraints like how's the roof oriented? How's the shading? Do you want to mount it on the roof or the ground? You might think it'd be easier to mount on the ground, but sometimes it's pretty predictable what's underneath on a roof. But what's underground is sometimes not very predictable. Learned that in an installation one time, and so these are decisions to make. I've seen them both places up in Massachusetts, and you have a nice yard with a little space. Nothing looks nicer than a PV system that's at the right orientation, facing south at the right tilt. Do you need some lead points for design to get up to platinum? Do you have some favorite components that you can't wait to install? Um, but some that you can get a special bargain on? Or is it just that your solar water heater doesn't run your refrigerator when there's a power outage? Um, Whatever the reason, and there's lots of them. So what should you expect from a properly designed installed PV system? Well, first of all, it has to meet all the electrical design and performance specs. And that's fairly straightforward to check that out and prove that after a month or so of operation. It shouldn't leak if it's on a roof, pretty obvious. It shouldn't blow away, that's also pretty obvious. I see a question, I'm going to get that in just a minute. It should be aesthetically pleasing, should last 25 years or more, and it should make the utility happy by complying with IEEE 1547-2000, because that's a way that PV owners actually help the utility. And what could be better than a partnership with the electric utilities where everybody wins? All right, what do we got? Are there fire hazard considerations regarding putting PV cells on the roof? Yeah, absolutely. Good question. All these are mostly local regulations, but there are IEEE and I'm sorry, what's the other one? NFPA, National Fire Protection Association, the folks who write the National Electrical Code. They have got recommendations for fire access. Most localities now have agreements with the firefighters. Usually it involves making sure you can walk across the peak of the roof and be able to get up to the peak of the roof. And usually you don't want to put modules in those locations anyway, because the wind loads tend to be higher at the edges of the roof. So there's another, and we're going to come to that thing, provision called rapid shutdown, where one flip of one switch shuts down the entire system. From right now, the rules are that if you have electricity coming out of the photovoltaic array, it can't go any further than the boundaries of the array, and there is no photovoltaic electricity anywhere else. So yeah, a lot of thought has gone into making sure the firefighters are happy. I can remember designing a megawatt system for Orlando about almost 15 years ago, where one of the main people who sat down at the table was the fire marshal, who we wanted to make sure we made him happy. So in general, folks are paying attention to fire requirements. Okay, so next slide here. Wait a minute, let's make sure there's nothing else. Okay, we're good. Let's look at a residential rooftop, and we're going to just stay with residential for the day, but keep in mind all these systems are scalable. If you can make a little one, you can make a big one. So yeah, all you do is, a big one is a collection of lots of small ones. All right, and it all depends on what kind of inverters you might want to use, but that will become fairly evident as we go. So what do we need? We need PV modules, obviously. We need racking to support those modules. And then we need a way of mounting the racking to the roof. We need an inverter listed to UL 1741, and the one that's listed to UL 1741, that's the UL testing standard to meet IEEE 1547. So this inverter converts the DC from the photovoltaic array to grid quality or utility quality alternating current for the grid. Have a bunch of code compliant disconnects and wiring, but that's all in National Electrical Code, various articles. 690 is the primary photovoltaic article, but then there's 705, and then you get back to 250 and so forth. And we'll be listing a number of the specific National Electrical Code articles that we need to pay attention to. We need a code compliant utility connection, and that's generally in National Electric Code section 705.12. Rapid shutdown provisions, and that's what we were talking about as far as fire protection. From on the ground level, you need to be able to shut down every ounce of electricity that's coming out of that array that is except for the modules themselves and within a couple of feet of each module. But otherwise, the rest of the building goes down if you shut down the main disconnect of the building. That then shuts everything else down. Some people say, why does it work that way? And the reason is because the photovoltaic inverters that are grid connected act as current sources. Now, a lot of people don't distinguish between voltage and current, but it's very important in this case because as a current source, it will deliver current to the grid only if there is grid voltage, because the grid voltage acts as a synchronizing signal. And if that synchronizing 60 hertz grid signal is there, then the inverters assume the grid is in good condition and they deliver their electricity. But if the frequency of the grid varies too much, or if the amplitude, that is, if the voltage goes too high or too low coming in from the grid, the inverter interprets this as a problem with the grid and it shuts down. That's what UL 1741 is all about. It verifies that the inverter has been tested to that and it meets the IEEE 1547 specifications. All right. You need a code compliant utility connection and rapid shutdown provisions, and we'll be talking about all those things as we go through. You're going to need a permit for it, and you're going to need a grid connect agreement with utility. And the grid connect agreements, they vary from jurisdiction to jurisdiction, from utility to utility. But normally they basically say that the utility will pay you so much for the electricity, and if the utility wants to shut off your system, they are allowed to do that at their discretion, but they have to give you a good reason for it. So, and some of them are 1 page long, and I understand some are as long as 8 pages long. And it seems to me that 1-pagers do a pretty good job of covering all the bases. Anyway, what are some of the types of straight grid connect? Well, I'm showing you 2 here. There's a string-fed systems, and if you notice what you've got here is just a bunch of modules in series. They're across that row of 8 modules on top. Those 8 modules are all connected, notice plus to minus, plus to minus, plus to minus, or minus to plus, whichever way you want to look at the direction. So the voltages of those individual modules add up, and the entire string has one common current. All right, problem with this is if one of these modules gets shaded, it doesn't want to put out as much current, and that affects the entire string. So that's an issue. There are lots of ways there people are fixing that now, but this is a basic system here to show basic system operations, and there are a number of ways of improving on these that we'll mention before we get through here at the end of the day. All right, and you see there's another 8 module string connected in series, and then those 2 strings are connected in parallel. And that DC goes down to the inverter. There's a DC disconnect, the AC disconnect of the inverter. Once upon a time, they put AC and DC disconnects both in the inverter, but now I haven't seen an inverter with an AC disconnect for a long time. The AC disconnect is generally external to the inverter and normally within sight of the inverter, and that's generally there for maintenance purposes, but it can also be used to shut down the PV system, because if you turn off that disconnect, then the inverter thinks the utility is gone, so the inverter shuts down. The only problem with this particular system, there's pretty high voltage DC right at the input of the inverter. And that's where the rapid shutdown system comes down, and that's incorporated now in most systems right at the module level. But that's not shown on this basic diagram. Notice the line from the disconnect goes to the bottom of the distribution panel. The idea is that you normally connect to a distribution panel with a backfed circuit breaker that is on the opposite end of the bus bar from the utility feed. And we're going to look at that in more detail later on and see why that is. And then there's the microinverter systems, and there's a whole lot more of those going in these days than regular string fed. The reason for this is partly because the microinverter meets all of the UL 1741 requirements, which means that if the utility is lost, that is, if the microinverter does not sense the presence of utility voltage, it will shut down right at the module. And the microinverters are mounted underneath the modules on the roof. All right, so that means you're shutting down the system right at the module if you turn off that backfed circuit breaker in the distribution panel. In a system like this, this is just a single string of microinverters. But even so, now the popular way of doing this is to put a microinverter combiner panel between the inverter feed and the distribution panel. And that simply allows you to have more than one string of inverters connected, which it combines and allows you to tie into the distribution panel with a single backfed breaker. But the other thing it has is the system monitor that you see there in that separate box that plugged in. That's the way they used to do it, but now they put the system monitoring equipment, which it goes right inside of that box I was just telling you about, the combiner box. And that, in fact, allows the manufacturer or the owner or whoever, maybe the installer, to monitor the performance of every single module on that system. And if something goes wrong, it raises a flag. If somebody goes out there, figures out what the problem is. So it's a very attractive feature of this system, is have that system monitor available. Okay, there's another system that doesn't show here that's using optimizers, and instead of delivering AC to the input directly to the distribution panel, they do maximum power tracking and then have a DC output. So the DC is connected in series, whereas the AC from the microinverters is actually connected in parallel. We have effectively a system of parallel connected current sources. We're going into more detail later on this, so at least I want you to know the difference between these two. And the optimizer system is fairly similar, but it also includes a main inverter at the end of a string or two of photovoltaic modules. Okay, moving on. Battery backup systems, just so you know what's out there. This is as much as we're going to do today on battery backup systems, but you can start with an array, and the array might have 6 or 8 source circuits in it. These are the small wires. They go into the source circuit combiner box and comes out with fatter wires. Now, what does this look like? That's just the opposite of a distribution panel, isn't it? The distribution, you come in with the fat wires and you leave with thinner wires. Here you come in with the typically number 10 or number 12, and you'll leave with probably number 6, depending on the size of the array. Nice to have a surge arrestor in the system to protect the electronics, because the charge controller has some fancy electronics in it. It has what's called maximum power point tracking. And what that does is it makes sure that the array runs at its maximum power, and we'll see what that implies in a minute. And Then the battery backup, well, that have to have storage batteries, and the charge controller is the device that controls how when the batteries may have to be shut down. Normally what happens is the batteries fill up, and any leftover electricity then goes to that battery backup inverter where it's used to power standby loads. If there's any extra left over, it goes back up to the main distribution panel, powers some more loads there. And if there's still some leftover electricity, it goes back out to the utility as indicated by the double-headed arrow up there that electricity can either come in or go out. And that's the scheme here with all of those arrows. Notice that from the array to the charge controller, it's a one-way path for the electricity, but once it leaves the charge controller, it has a lot of options into the batteries, back from the batteries, into the inverter, back from the inverter. And then the standby loads, there's only one path to the standby loads, but their electricity can flow in both directions from the main distribution panel. Okay, so that's the DC coupled system. And then there's another system called AC coupled. And this is one that if you decide you want a PV array and a direct grid connected inverter, and so instead of going to the standby loads, the way this shows that direct grid connect may have gone straight to the main distribution panel. But then maybe a year or two later, along comes the ice storm or the hurricane, and you notice you don't have electricity. And without having to replace that direct grid connect inverter or PV array, you can add an additional standby panel. You can add an additional source of renewable electricity if you want, or for matter that wind or low head hydro inverter, it could actually be a generator. And that then gets fed into the battery backup inverter because of a not so well-known secret that the AC out terminals there can actually are bidirectional. You can get AC out of them, but you can also put AC into them because there's this straightforward bus bar between AC in and AC out that simply has a disconnect that shuts off if the utility is lost. So with this system, if the utility is lost, then the main distribution panel goes off, but the battery backup inverter simply opens a connection between the battery backup inverter and the main distribution panel, but still is there to serve the storage batteries. And the storage batteries could very well, in this case, be a power wall, and the battery backup inverter is incorporated as a part of the power wall. Okay, so that's a rough summary of what's out there, that the kinds of system you might consider. Let's look at some structural things first. Okay, and this is to make sure that if there's mechanical engineers in the group that you guys are going to be happy. Even civil engineers are happy to read this, so make sure. Usually the design starts with the module itself. And I indicate that, hey, it's not unique. It doesn't always happen that way. Maybe you've got a nice 10 kW inverter you wish you could put to use. So you design around the inverter. Excuse me, I'm going to mute myself for a minute and get rid of that cough. I'll be right back. All right, that was a nice cough. Okay. The modules themselves have to be listed to UL 1703, and 1703 gives electrical and structural requirements for the modules. They have certain electrical properties that we're going to look at because they're relevant to the mechanical design of the system. They have thermal properties that are also relevant to the electrical design. They have structural properties that are particularly useful and important to the structural design. So let's take a look at some possible criteria that might be used for selecting modules. Maybe we like a particular manufacturer. Maybe we want it tomorrow. and not everybody can necessarily deliver immediately. Maybe we want the super efficient ones, because the more efficient the modules, the more electricity you can install on your roof in the same space. Cost per watt. That's pretty constant. And right now, folks, it is in the range of 50 cents a watt and sometimes less for a module itself. Dimensions of the module. Right now in 2020, there are basically three sizes of modules. There's a 60 cell that's about 1 meter by 1.5 meters. There's a 72 cell that's still about 1 meter wide, but a little bit longer. And there's a 96 cell that's, I think they are eight cells by 12 cells. So so they're all based on individual cells that are connected in series for the most part. Occasionally there are series parallel connections possible, but most of the time these cells are all connected in series, each cell contributing about 0.5 volt to the DC output of the module when it is operating at maximum power. So in that case, at 0.5 volt each, it means that a 60 cell module operating at full power will be putting out about 30 volts. And that's not a whole lot, but when you put 10 of them in series, then you get 300 volts. Put 20 in series, you get 600 volts. So you can get pretty high voltage by just stringing these out in series. All right, thermal performance is important because as it gets colder, these things actually produce more electricity and their output voltage increases. As it gets hotter, they produce less electricity and their output voltage decreases. So that you need to take that into account in your system performance analysis as well as in your design calculations. The aesthetics, you can get different colors. You can get modules now that have black rims or aluminum colored rims. And so, you know, if you're fussy about what it looks like up on the roof, there are some options available now. The certifications and the listings are important, of course, and that's mostly the UL 170, what did I say, 1703, whatever we had on that previous slide. And but the other part of certification is how much is it certified for? How much uplift will it withstand? How much downward pressure will it withstand if you're worrying about a snow load and so forth? So they'll be listed to UL, but the UL has minimum standards, and a lot of the modules out there are now exceed the minimum standards. There are some places where some modules, the manufacturers make it a point that they recycle all the leftover materials and they don't have any ponds of things that they use to make the modules sitting next to a schoolyard somewhere. So people who are sensitive to that, you can find out how green the manufacturing process has been. And a warranty. Well, it's almost every listed module out there is warranted for a minimum of 25 years performance. And at the end of 25 years, they don't just turn into a pile of dust, but they have at least 80% of their original performance. And most they're finding have more than that, to the extent that you can hardly measure any degradation over time on them. So if you do your economic analysis based on 25-year lifetime, well, guess what? They're probably going to live a lot more than 25 years. So that's important to know. And they are warranted for 25. Okay. So here's, it's kind of useful to know something about the electrical properties. Here you see that the amount of current available from a module is almost directly proportional to the amount of sunlight shining on it. Okay, if you're below, say, about 14 volts or so. And even if you're up at 18 volts, you're still pretty much proportional, but the amount of current available at 18 volts isn't quite as much as the amount of current available at 12 volts. The amount of current that's available at 0 volts, which is if you short circuit the leads on the module, and don't you dare try to do that on your car battery, but if you have a module, you can actually short those leads and connect them directly together, and you don't get any big sparks because your current is limited to that so-called short circuit current. All right, which is the current that flows when you short out the two module leads. And you notice the short circuit current is still about the same amount of current that flows at 6 volts across these particular modules. And then out there somewhere around 21 volts, you'll notice that all of a sudden there's no more current available. And that voltage where the current is 0 is called the open circuit voltage. And you notice the open circuit voltage is not directly proportional to the amount of sunlight. All right. Now, those of you who are really good at reading graphs, and I'll usually ask this question, but I'm just going to make the statement here, that open circuit voltage is proportional to the logarithm of the intensity of the sunlight. Okay, so it only goes up very slowly as the sun gets brighter. All right, there's other things here, and you know, somewhere obviously power is equal to current times voltage, so at short circuit, there's no power being delivered. And at open circuit, there's no power delivered, but certainly in between there's power being delivered. And it's a little easier to see that if you look at a plot of power versus voltage instead of current versus voltage. And notice that at all these various levels of sunlight, there is a maximum power voltage, which is almost the same. All right, that's called the maximum power voltage. And at that maximum power voltage, there is also a maximum amount of current that flows. And you can go back to the other chart to find out how much that is. All right, but you can see where that maximum power is. And notice that this would be a 150 watt module because they test these at standard test conditions, which are 25 degrees Celsius. And a kilowatt per square meter of incident sunlight. They use a xenon flash lamp though, but this is a 150 watt module, which is only about half as big as a typical module that's out there these days, 1/3 as big as some of them. Okay, but these maximum power points are important because you want to track them. That's the way you get the most money out of your money's worth out of the modules, is by operating them at peak efficiency. So that's what we're talking about here. Maximum power points is where you get the peak efficiency out of the module. All right. How does this relate to the structural? Well, it just has to fit in there somewhere because everybody should know about it. All right. And most charge controllers and essentially all grid connected inverters and optimizers, which is a new kind of a device that's used that we'll talk about later, they all have electronic maximum power point tracking within the device. And it's at the DC input coming from the modules. Okay, so maximum power point tracking is pretty straightforward electronic circuit design. and lots of stuff. There's essentially no system out there being designed now, unless it's something really, really small, that doesn't take advantage of maximum power point tracking. The other thing that's important to know is that the performance of the modules is very much temperature dependent. This 150 watt module is represented by the green line, which is a performance at 25 degrees C. But if it cools down to 0 degrees C, 32 Fahrenheit, which it might be earlier in the morning, if it's 32 degrees Fahrenheit and nice and sunny, that module is going to warm up because it is black color and it absorbs lots of sunlight, and 20% converts to electricity, and about almost 75% is going to be converted to heat to warm it up a little bit, which is good in the winter because it melts the snow off. Okay, and you can see that at minus 25 Celsius, the module peak power jumps over 180 watts, whereas 50 degrees C, which is more typical operating temperature for these modules, the power drops down to in the range of 130. So that's why it's useful to use the performance per year metric to evaluate what power that's going to come up, because rarely does a module actually operate at its maximum rated power. So you need to look at your annual amount of kilowatt hours produced to make a reasonable economic analysis of the system. So if you want some numbers, about 0.47% per degree C is the way the power decreases. It's a negative coefficient. The bottom line is you want to keep it cool, which is why you generally want to use a racking system that gives you a couple inches of open space underneath the modules, and hopefully not so much space that cute little animals will want to hide under there to stay warm. I've heard that in some of the northern climates, that's a popular thing. I gather up in Ontario in particular. Here's the question. Let's see what we got. This is not clear to me. Why is the power higher for lower temperatures? It's part of the physics of the devices. And that's a long answer. Part of it, as the cell itself gets hot, its performance goes down. And that's the best answer I can give you now. But the physics of it, if you want to read, there's a book called Photovoltaic Systems Engineering, and chapter 10 goes into gory details of the physics. All right, so that's the best. I'm not surprised it's not clear. What it's mostly, if it's just a surprise to you for now, you'll be able to check that out with another reference. All right, I wish I could do better, Carol, but in a way, this is a good thing, because it means in the northern climates, even though the sun may be lower in the sky, you're compensating for that by having your modules running cooler and more efficiently, so you can compete well with the systems in the lower latitudes. Okay, click a couple things here, back to this picture, and click again. Okay, so let's do a design. Let's pick a module. This is an old one, 280 watts. That same module of this size now at 20% efficiency, probably be in the range of 330 watts. But it doesn't make any difference. You just put in a different number when you do the design. So this is the idea of the design, what goes into the design, and I can tell you that a lot of all these decisions are just being made by a computer program. And what's important is the engineer understand what to expect the output of the computer program to look like, because there's always a possibility of garbage in, garbage out. So once you see that final result out of the computer, it's got to make sense. and understanding how these things work helps you to be able to make sense out of what you're seeing on the output of the computer program. So this thing withstands 113 pounds per square foot, and that's a lot. Yeah, it's a lot of snow load. If you figure out a cubic foot of water is 62.4 pounds or something like that, and that would be, so that could have 2 cubic feet of water, one on top of the other, and if you incorporate that to snow, that's awfully deep snow. So 113 pounds per square foot, the upward pressure is not necessarily the same, and in lower latitudes and a lot of other places, it's the suction pressure, or the pressure up. It actually exceeds the downward pressure load on a module. So you want to make sure that the upward pressure meets the wind load in your area. Just to make sure the civils are happy, you'll all recognize this coming out of ASCE 7, and where it defines the various wind load zones on a roof. And zone 1 is the interior there, the white part, where the pressure is the least. Zone 2 is at the ends or the edges, and there's a little more pressure there. Zone 3 is at the corners, where it's worst of all. And so in general, if you're going to put a module in a corner, it has to be fastened down a little bit better than it does in the zone 1. There's this parameter A. And okay, so fine. The width of that zone 2 depends on the parameter A, which is 10% of the least horizontal dimension, or 4/10 of the height, whichever is smaller, but not less than 4% of the least horizontal dimension, or 3 feet. All right, read that 10 times, and if you understand it, well, it takes a little while to do all the if-thens in that prediction, but fortunately computers are happy to do that now, so it's just conditional statements. But these are things you need to pay attention to when you're designing your racking that's going to hold up the system. All right, so then you fit them on a roof. You get a nice scale drawing of the roof. You fit the modules on. If you can put them all in zone 1, then it's less expensive to mount them on a rack. But right now, because the modules are so cheap, it's worth it to spend a little extra money on racking and let them slip into zone 3 and 2, as long as you maintain your fire access, as was mentioned earlier. So this is just a simple design here where we got 5 and what do we got, 9 there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 14 modules, all pretty much in zone 1. And what can we do with those 14 modules? Well, let's take a look at performance here for a minute. This is from a simulation from the National Renewable Energy Laboratory System Advisory Model. We're going to mention the simulation and performance later on. So suffice it to say that in Tampa, your best orientation is south-facing with a tilt of 25 degrees. But if you go 15 degrees either direction, the worst you do is lose 4%. If it's more flat. But you're also looking at the amount compared to 100% performance with a lot of other orientations here. Now, this is for Grid Connect and for annual performance. If you've got a standalone system, then you may want to pay a little more attention to the tilt, because in the winter you want it to be tilted up higher. In the fall and spring, it's best if it's tilted at latitude, if this is your cabin up in the woods northern Maine or something like that. In the summer tilt, you want latitude minus 15 degrees for maximum performance. But otherwise, it doesn't make a whole lot of difference of where these things are facing, other than the last thing you want to do is then have them on a vertical wall in Tampa, because you lose 45% on that deal. So let's move a little north, Atlanta. Optimum tilt, 35 degrees facing south, but other directions make it 15 degrees flatter, 20 degree tilt. You only lose 1% on the year, and that's because Atlanta has got more sun in the summertime. You're taking advantage of that summer sun, but with a 20 degree tilt. But it means in the winter, your performance is going to be degraded. So, but if you're just talking about annual electricity, and your roof has a 22 degree slope or something, then you're just going to mount it directly parallel to the roof, which is normally the way you're going to mount your system. Tilted panels on sloped roofs are essentially not done, except for some folks up in Yellowknife, as you saw earlier. Got to check the time here. Let's see, we're at 10:59. Okay, we're doing okay. Let's see. Other information. It's 60 degrees outside now. Gee, warming up. We've got a little cold weather this last week, and my building had a leak in the natural gas, so we don't have any heat for the building. It's about 70 degrees inside in my office here right now, but that's a nice temperature. I just wear 3 levels of sweatshirts and so forth. Okay, enough of that editorializing. Atlanta, let's take a look at Albany, which is probably a lot more relevant to those on the, and notice in Albany, ultimate best tilt, 30 degrees facing south, gives you your maximum annual performance on an array. But at 45 degrees, you only lose 1%. At 60 degrees, you lose 7%. Okay, but you can read the graph, so I don't need to go through this whole thing. But in any case, it shows you what percentage of optimal you get with an assortment of different orientations and tilts in Albany, in Atlanta, and in Tampa. And if you order up a copy of NREL SAM, it will give you these. And by the way, it's free because it's paid for with taxpayer dollars. And it's a real nice program. And if you order that, we'll show you some of the results later on. Okay, what are the factors that contribute to wind load? I'm going to click through this quickly just so we know what they are. Okay, and these are all things you'll take into account when you calculate the wind load using ASCE 7. Okay, and your wind load, depending on your wind speed, wind load's proportional to the square, their wind speed modified by a whole lot of different constants depending on orientation, roof slope, and all these other things that are on the list of yellow print here. This is what figure 30.5-1 looks like in ASCE 7-10. You'll see let's look at the roof slope 0 to 7 degrees in zones 1, 2, and 3. The EWA means effective wind area in square feet, and they have a number of different possible effective wind areas. The 10 square foot effective wind area, it gives you the highest pressure, so this is a maximum. And notice 110 mile an hour wind, downward pressure in zone 1 is 8.9, and in fact it's 8.9 in all three zones, but the upward pressure, the lift in zone 1, varies from 21.8 pounds per square foot to 55 pounds per square foot in zone 3. If you go to 140 mile an hour wind, you're up to 89 pounds per square foot uplift in zone 3 with the 0 to 7 degree slope. But notice as the slope increases, the uplift in zone 3 decreases from 89 to 83, and in the 27 to 45 degree tilt, it drops all the way down to 41, which is only half as much as in the 7 to 27. So roof tilt makes a big difference in terms of the upward lift forces on these modules. So again, I tell people who are designing PV systems, in addition to your fancy computer programs, make sure that on your desk right next to you is ASCE 710, and whatever version of the National Electrical Code is applicable to the jurisdiction for which you are doing the design. These two books get you through a lot of design. Just some pictures of some of the hardware, an L bracket holding up a mounting rail. Notice in the lower left, there's the clamp that provides a separation of about 1/2 inch between the modules. And in the lower right is where it holds down the modules. And notice that there is not very much sticking out, because even a slight shadow from that bolt can affect the performance of the module. And it's nice when the clamp is in the corner there, because that shadow, it's harder for it to fall across any one of those 4 adjacent cells. All right, and all these commercial mount manufacturers have all their mechanical and structural specs. They tell you what's the maximum mounting separation between the mounting brackets, and it's right there on this 2-page front and back specification sheet. And so again, the numbers, this is just a lot of looking up the numbers in the table to find out what works or not. If you want to use the formulas that show some bunch of constants times the square of the wind velocity, that's even more fun for the civils and the mechanicals and the group, and the electricals ought to give it a try as well, because it isn't all as bad as it might seem. Okay. Force per mounting foot. Let's see if first you put some mounting feet. You notice the way these are the mounting feet you see here. A nice way of doing a design is to use alternate trusses to make sure that every truss is bearing some part of the total load of the system, and that's why we've got the mounting feet at not exactly on top of each other, because that would mean we'd be skipping some of the trusses. So we've got a total of how many brackets here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3, 6, 10, 30 brackets. If the modules are, say, 15 square feet, most of them now are about 18 square feet, but again, you know the module dimension and you multiply them out and you get your area of the array. In this case, we got 90 square feet. If the wind load is 80 pounds per square foot, again, if it's 90, you multiply by 90 instead. But in this particular case, we got 7,200 pound total upward lift wind force on this array, and you divide that by the 30 brackets, and that boils down to 240 pounds per bracket. So now, what does it take to hold down 240 pounds? So we take a look at lag screw withdrawal loads, and depending on the lumber, and down where I am here in Florida, we've got other yellow pine trusses, but if you have white spruce or Douglas fir, they don't hold quite as well. It's a little less dense wood. But if you're using 1/4-inch screws, you get 281 pounds per inch of thread penetration into the truss. If you're using 5/16, which is the most common lag screw to use, you get 332 pounds per inch of thread embedded into the truss in southern yellow pine. Notice I use the word truss and not the plywood decking. The screws have to go down into the trusses to get these ratings here. All right, if you're using Douglas fir, you drop from 332 to 198 pounds per inch. So for the design at hand, what have we got? If you use the 5/16 lag screw, it only has to go in about 3/4 of an inch into the truss in order to get your 240 pounds of pull. If you're using a 1/4-inch lag screw and a white spruce, then you need to go into the trusses by 1 1/4 inches. And all the designs we have here, for any typical kind of a roof, whether it's a tile roof or a shingle roof with trusses and residential type design, pretty much all of them just come out specifying 4-inch lag screws that gets through the thicknesses of the mounting feet and the roof decking and getting down through the into the truss, and it very much exceeds the 3/4-inch penetration. Typically, it's 2 inches, 2 to 3 inches. So pretty straightforward stuff. Even for an electrical engineer can figure this kind of stuff out. And we're going to show here now how mechanical engineers can figure out the electrical design details. All right, so what are the types of straight grid connect systems again? The string fed and the microinverters. So we're going to take a look at them both and do a standard design where we have to figure out what are the wire sizes and so on and so forth. And what are the conduits and what kind of D ratings do we use? And so this is going to be gory detail here, folks. And it's there because if you decide you really are interested in it, you'll know that it's there as you go back and review it again in the slide set if you order it up. There's no extra charge on that. So I encourage you to take it, use it, share it, whatever. Like I say, we need lots of engineers getting involved in PV over the next 10 or 15 years, since the systems have now become more than cost effective. It's one of the best investments you can possibly make. So people are going to catch on sooner or later, and there's going to be big demand. So just keep that in mind. So let's go to a source circuit is the connection of the leads of the modules that will connect in series for a string circuit, okay? And so first of all, we determine how many modules fit on the roof. We already did that. We can fit 14. And then if we've got string inverters, if you use more than one string, it's a good idea to have all strings the same length, that is the same count of modules with the same orientation on modules, with the very important unless that optimizers are used. But if you use optimizers, that restricts the inverters you use. The inverter has to be one that talks to the optimizers, because there's a lot of communication going on in the process of optimizing the performance of the system. The optimizer, though, is also good in this system because they are perfect for serving the function of rapid shutdown. And again, that's fire requirement for the most part, a safety requirement. And the optimizers are located underneath the modules, but they are DC to DC, but they shut down if the DC flow is interrupted to the inverter. Okay, for a module, you need to calculate the maximum open circuit voltage. And since open circuit voltage is temperature dependent, you need to use the temperature coefficient for the module that is on the data sheet. And it can be as high as 15% if you 15% higher than the standard test condition, 25 degrees C. So it's a good idea to do the calculation. But again, this is normally done by a computer program. And then by doing that, this determines the maximum numbers of series modules, because the inverter has a maximum input voltage. Some are 600 volts, some are 1,000 volts. So you need to know that information about the inverter. Okay, used to be 600 was it, but now since about 2014, we're allowed to have 1,000 volt strings up on the roof of DC. Then the next thing you do, after you calculate the maximum value of the open circuit voltage, then you have to calculate the minimum value of the maximum power voltage. That's the voltage where the power maxes out for the module. And that can be as low as 85% of the standard test condition maximum power voltage. You saw that in the graph that we presented earlier. Then the minimum number of series modules using the maximum power, that determines the minimum number. If you go less than that, your voltage of the string won't go high enough to be affected by maxing out the power from the string. So you need to make sure you meet that criterion as well. Now, again, this is what is oftentimes done automatically by the system that you install. And this is something we had to do all the time 10 years ago and 5 years ago, but now the systems are getting smarter and smarter. So all this rigmarole of calculation is being handled automatically these days. And all you need to understand is what the constraints are here, and make sure that once you put your information in, that you get sensible information coming out. All right, so you probably won't design using all this detail, because it'll already be taken care of for you in whatever program you buy. All right, here's a question. Let's take a look. Will I be talking about the system design software you use? Well, to be honest with you, I just review, and there's a software. Let's see, what they told me what it is, though. I think it's PVCAD or something like that, and there are others. Like I say, I'm a retired guy. I'm 77 years old. The last system I actually designed was back in about 2012. But I've been trying to keep up with what's going on. But I can't remember the names of all of the software. And but I think if you Google photovoltaic system design software, you'll probably get the answer to that. And there's more than one kind, I think. There's some that do the mechanical, some that do the whole thing. Believe me, after the session is over, I am going to be making a phone call to find out, and I'll see if I can somehow get that posted, or get that answer back to you through the host. All right, and I'm sorry, that's the name of that particular software. I don't know specifically, other than I'm pretty sure it's something like, it's like AutoCAD, but I think it's called PVCAD. made by the AutoCAD people. And it's got nice designs that you tell what module you're going to use, and it automatically can populate a roof for you. It's nice stuff. The intent here this morning is to let you know the basics of the design, and the next step is to find out what's being used in your area and what's being accepted by the authorities having jurisdiction. But thanks for asking that question. It's one that I knew the answer to 2 days ago, and now it slips my mind. I should have written it down. Okay, let's see. So let's actually do this. All right. And then we calculate the total array power at standard test conditions to confirm the inverter size, because once you know the array size, we then need to find an appropriate inverter to go along with the array. Okay, so take a module. Here's one that we had before, and notice here it shows the temperature dependence. It gives open circuit voltage, short circuit current, maximum power voltage, which is at about 80% of the open circuit voltage, maximum power current, which is about 90% of the short circuit current, and that's pretty close, but the algorithms that they use in the maximum power point trackers do a whole lot better job than that. They just do a little iterate, they measure the power, and then they move the voltage a little bit, measure the power again, and they'll decide whether up the voltage or down the voltage. This is all done with the DC to DC conversion devices, and they've been at it for a long time, and they've really got it down to an accurate science. Oops, how did I do that? Let's back up here. Wait a minute. Okay, and again, the module listed the UL 1703. These are the numbers that apply to the module. So now let's put it in and let's calculate what are the voltage extremes. Let's say the inverter can handle 175 to 600 volts. That's fairly standard for a straight string inverter. And if the coldest is minus 20 C, and that's not unusual for up in the New York, New England area, then the temperature difference between standard and minus 20 is 45 degrees. And the formula for that, the open circuit increases from the starting point, 38.1. Then you add to that the 45-degree temperature difference times the coefficient times the original open circuit voltage, and it rises from 38.1 to 43.76. All right, so we keep that in mind. Divide 600 by 43.76, 13.71. That means we need to round down, and 13 is the maximum number of modules we can have. Otherwise, if we put in 14, we'd go over 600 volts at that cold temperature. And the issue there is simply that the inverter electronics are designed to handle 600 volts DC and not a whole lot more than that. So you could damage the inverter if you were to throw in that extra module. All right, now what about the high temperature? Want to make sure we track that maximum power point. Well, if the hottest temperature would be 65, and we say, oh my gosh, 65 degrees C, 37 is normal body temperature, that's awfully hot. Well, again, keep in mind that these things are black and they absorb sunlight, and about 80% of it turns into heat. So they get much hotter than ambient, maybe as much as 45 degrees above ambient. So if ambient is so this is the hottest module temperature, all right? And you can estimate this using the information on temperature performance of the module that's on this 2-page module data sheet. Again, here we got temperature difference is 40 degrees C. So we plug that into the formula, and we start at 30.5, and we got 0.11. These are volts now, not percent. Notice that you got to be careful of the units. And so the bottom line is your maximum power voltage drops from 30.5 down to 26.1. Plug that in, 175 is the minimum value you want for that string voltage. So divide that by 26.1, gives you 6.7. This time we round up because anything under 6.7, it gives us too low of a output voltage, so we have 7. So that means in this string, we can have anywhere between 7 and 13 modules, and the inverter will be perfectly happy because the voltage range of the output of those in series will fall within inverter input specifications. All right, so we can summarize possible configurations here, but we have 14 modules, and with 14 modules, we're going to need 2 source circuits because we can't have 14 in one circuit, we can only have 13, but we can have 7, so therefore we have 2 groups of 7, and that will give us 3,920 watts from that array of 14 modules. All right, so it's an easy table to draw. And the only part we really need is the part for 14 modules. All right, so looking at the inverter specifications, 3,920 watts, 2 source circuits. Your inverter has to be listed to UL 1741. This particular one has maximum input of 600, MPT range of, let's see, what did we get here? Oh, we've got something on a, let me just take a look what just popped up. It was in the chat. Is the audio off? I no longer hear anything. Well, let me take a look. We need some answers on that one. Carol says, okay. Matthew says you can hear. Anybody else want to comment? We're in the chat box now. I'm not sure what kind of computer you're using, Carol. Oh, you're back on. All right, good, good. Every once while I tell a stupid joke, so I hate for you to miss any of them. And thanks for asking, and thanks for the help from the rest of the group on that. Yeah, if you have a technical issue, definitely go to the chat box, and we will try to respond as quickly as we can. Okay. So here's an inverter. What else are we doing? It's maximum input current 24 amps. Well, we're good because the modules themselves, the current is somewhere in the neighborhood of 9 amps. So the 2 strings in parallel is around 18, so we're good on that. Maximum continuous output current of this inverter is 16 amps. And that's an interesting number because 125% of that is exactly 20, which means you can have a 20 amp circuit breaker. And the maximum efficiency of this inverter is 97.5%. That's interesting to know because the inverters are very efficient, and some of the new transformerless models are pushing 99% efficiency. So it's amazing at the efficiency. Imagine an automobile engine operating at 97.5% efficiency. Output voltage of the inverter is 240 volts AC, and straight 240, not 120 240, but straight 240. So it connects to L1 and L2 in the panel. All right, so we look at our roof. My gosh, we have 14 modules, so we've got a 3,920 watt array. Maximum voltage is going to be 284 volts. Minimum is going to be 183, fits nicely into the inverter spec. So, you know, this is where the intuition comes in really handy. You want to feel comfortable that 7 to 13 modules is going to fit into this system. And regardless of the kind of system you're talking about, whether it's yesterday's or tomorrow's, you need to develop this intuition as to what the right answer needs to be so that something that says you need minus 13 modules or something, it'll ring a bell and say, wait a minute, what did we do wrong here? Okay. 1741. Now let's talk a little more detail on UL 1741. First of all, the requirements on the waveforms. This is in order to connect to the utility, you have to meet the UL 1741 details. So it has to be a good sine wave defined as less than 5% total harmonic distortion, and it specifies maximum amplitudes for all harmonics. Right now, every inverter I'm aware of that's on the market is better than utility sine waves, because sine waves are generated by rotating machines. And when you have rotating machines, your design of the machine itself makes it extremely difficult to have a perfect sine wave. You come pretty close. So electronically, you can actually do better than you can mechanically in terms of sine waves. Have to have disconnects, and this is the inverter itself has to automatically do this. If it's over or under voltage, or if it's over or under frequency, and the limits are specified, it's something like 10% over and 10% under on the voltage, something like less than 10, about 1% under or over on frequency. If you're 60 hertz, you drop down to 59.4, and I think you have to disconnect. It's somewhere like that. It's easy enough to find out what those requirements. And for the most part, you don't worry about it, because as long as the device is listed as UL 1741, it's already been tested and proven. And so you don't need to say anything in a set of plans other than inverter is listed to UL 1741. And anti-islanding is the interesting thing, because what if you've got 4 different neighbors, each of whom has a 5,000 watt photovoltaic system connected to the grid, and the grid goes down? How do we make sure that neighbor number 2 doesn't think, or the PV system of neighbor number 2 doesn't think that the PV system of neighbor number 1 isn't the utility? And the secret here is the fact that these inverters are current sources, all right? And they have to be synchronized by the utility. So without the utility voltage to synchronize them cycle by cycle, within about a second or so, the frequency drifts beyond the allowable limit, and the inverter automatically shuts down. And this happens for all 4 of those inverters. So within less than 5 seconds, all 4 inverters are shut down. And this makes utilities happy, because no utility has ever documented being able to get a repair truck out in less than 5 seconds. So nobody's ever been hurt by having a PV on the line when somebody wanted to fix it. Okay, array wiring. And I'm going to go through this kind of quickly here, but just so you'll know that it's here in the presentation. The modules themselves connect in series with locking connectors, and there are plus connectors and minus connectors, so you can't screw it up no matter what you drank the night before. Your biggest worry is not in connecting the modules properly, but in making sure you don't fall off the roof. When you wire up your string, you ultimately, these are open wiring, by the way. There's 2 types of wiring allowed for open source circuits, and that's PV wire and type USE-2. And and mostly right now, the insulation that's being used is type PV, like in photovoltaic. It's rated for open in the sun exposure. It's got UV resistant insulation. And it saves you the problem of having to run conduit from module to module. Once upon a time, right around 2000, you had to run liquid tight from one module to the next. And boy, that took a long time. And no more of that stuff. They got over that in a hurry. Very simple, straightforward connectors, one module to the next, click, 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 down the string you go, and you're done. Okay. Conduit runs through a building. See, from the rooftop junction box, you then splice the open circuit wiring to conductors in the conduit. And then you need to do some derating due to the temperature on the roof and the number of conductors in the conduit and so forth. Anything carrying DC through a building is supposed to be metallic. There's now some reasons why it can be with rapid shutdown, it's now not quite as essential to have metallic conduit run. You can run PVC. Generally, you can convince the local jurisdiction that PVC is a better deal. Well, sometimes it's not. Sometimes it doesn't hold up nearly as well in an attic as uh, EMT, but in a saltwater environment or something, there are certain environments where metallic conduit doesn't hold up very well, and PVC is a whole lot better. So talk to the local authorities on that one. Um, Conduit ends at the inverter or maybe at the AC, or there may be a DC disconnect ahead of the inverter, but usually not. And the rapid shutdown provisions need to be made within 10 feet of the array according to the 2014 code, but they need to be made a lot closer according to the 2020 code. But there's a lot of out there to be able to meet this requirement at this point. And so nobody's having any problems with this. And the nice thing is that the code is, it's a performance specification as far as rapid shutdown. So it's up to the designer to decide what kind of rapid shutdown they're going to use. It just has to work. That's all. That's the requirement. And it has to work within about 2 feet of the array, I think, is the current requirement. So here's our design of our circuit. And notice I did this on purpose because the module manufacturers, if you're just connecting straight grid connect, are pretty smart in terms of how long they make their leads on the module. And you can see that I can skip over one module there from the upper left to the third one in from the upper left. I can connect a minus to a plus, and then I can hop over another module and hop over another module. And all I have is most of the wiring is just the module wiring that's already built in on the modules, and just a couple little extensions there at the end going to the junction box for these two strings. All right, so then down the string to the inverter, it's got a DC disconnect, it's got a ground fault detection interruption, it's got source circuit combiner, it's probably got arc fault protection as well. Then the enter goes to an inverter AC disconnect to a distribution panel with the point of utility connection then is in the distribution panel by a backthread circuit breaker. A note on that circuit breaker, if you turn that circuit breaker off, the PV system thinks the utility is dead, it shuts off. So therefore the load side of that breaker, which is where you're feeding the PV in, there is no voltage on that load side of that breaker anymore if it's turned off. And from the point of utility connection to the utility. And of course, you can always do line side taps, load side taps, and following all the tap rules if you don't have room in the distribution panel for your point of utility connection. Okay, wire sizes and types. And again, I'm going to click through this relatively quickly. We're at 1133. National Electrical Code spells it all out. It's nice if you can limit the voltage drop to less than 2%, but in general, NEC allows 3%. So, but it's not that difficult to limit your voltage drop to 2% because oftentimes you got multiple conductors in a warm conduit, so you have to derate. So it makes it, you'll be using bigger than usual conductors oftentimes. So being less than 2% is almost always the case, whether you tried for it or not in a residential. But if you're in a bigger commercial, then you need to pay some attention to voltage drop and the length of wire and whether you need to make it a little bigger. Need to do all your derating, ambient temperature. You need to do conduit fill deratings, and they're all specified very clearly in the National Electrical Code. Open wiring at the modules, PV or USE2, we already mentioned that. Conduit is usually THWN2, that's resistant to all kinds of stuff, plus it's 90-degree wire. Then wiring between the inverter and the point of utility connection. Again, 125% of the maximum inverter output current. So here we got 16 amps out, 125% of that is 20 amps, so that means that you can backfeed a 2-pole 20 amp breaker. And that 2-pole 20 amp breaker will normally be located on the opposite end of the bus bar as the utility feed. And we'll draw a picture of that in a minute and show the reason. So for the inverter output wiring, normally there's no ambient or conduit fill correction. Sometimes folks here are using a 0.96 conduit fill, though there's only 2 current carrying conductors, so therefore you're at 100%, and 96% or 0.96 if you're up over certain temperature for wire sizing. And it all depends on where that piece of conduit is, whether you do the 0.96D rate. So in this case, number 12 at the output to a 2-pole 20 amp circuit breaker is probably good. You can check the distance. Here's the formula for it. I knew you'd all want to have at least one formula. So the maximum distance is the percentage voltage drop that you're willing to accept, and that as a number, 246, not 0.02, not 0.04, because that's all taken care of in that 0.2 in the next term, times the operating voltage, 240, times 0.2, times the operating current, 16, times the ohms per 1,000 feet of that wire, which you dig out of the chapter 9 of NEC, or the, in the tables. And so if you're using number 12, put in the numbers, 1.93 ohms per 1,000 feet means you can go 77.7 feet between the inverter and the point of utility connection with number 12. If you put in number 10, then you can go to 124 feet. If you go to 690.64, which is the same as 705.12 now, but once upon a time it used to be 690.64, there's lots of rules for where you can connect to make this point of utility connection, okay? and here you can read this. You can connect to the load side of the service disconnecting means, or you can connect to the line side of the service disconnecting means. You just need to follow proper tap rule connections. And you follow 705.12 D 1 through 6, and that gets you there. All right, and this is a blessing when that finally came out, because there was a lot of confusion up to this point about exactly what's okay and exactly what's not okay. But 705.12 in National Electrical Code now, and especially in 2020, if your jurisdiction is using 2020, makes it very clear about all kinds of oddball ways you might tie into the utility, depending on exactly how that distribution system comes in from the meter. Sorry, one of those coughs again. Here's an example. You notice down at the bottom, we're feeding the bus bars from the bottom with 12 amps from the PV system, kind of a small system. But it also shows the loads on the bus bars. So without the PV, you're going to have 143 amps on line 1 and 129 amps on line 2. But as you're feeding backwards, you're making up 12 amps on each of those 2 lines. So that's 12 amps that doesn't have to come in on L1 and L2 from the utility. So you're actually doing a favor to your bus bars by tying that PV in at the bottom, because it reduces the load at the top by whatever amount of PV is coming in at the bottom. And many of you may have, I can remember going into more than one place and putting my hand on the panel above where the main comes in and feel heat, open that panel cover, and sure enough, there's a bad connection that got hot. So the less current, the less I²R heating, better performance of the panel. So people who say, oh, PV messes you up. No, sorry guys. PV is good for your panel distribution, and because it actually reduces the total amount of current required by L1 or L2. And this is all in 705.12. So there's a calculation you make that says that the sum of the PV breaker plus the main breaker has to be less than 120% of the rating of the bus bar. And that almost always happens. Okay, overcurrent protection. Again, I'm not going to spend a lot of time on this because it's all in 690.9A. All right. And You just follow the rules. And the important thing is here, 690.9A has changed a couple of times between 2014 and 2020. So that's why you just don't follow the rules here that you see in front of you. You take a look and see what 690.9A says right now for what's going on in your particular jurisdiction and follow that rule. Okay? At the inverter output, I don't think we're going to see this change. 125% of the maximum inverter current for the wire sizing. And that's also a good idea for the sizing of the overcurrent protection. Disconnects, yeah, you need that, the inverter input and output. The input generally is a part of the inverter. The output is oftentimes a separate disconnect, but hopefully within sight of the inverter, because that's the whole idea, is for maintenance purposes. And have to keep in mind that the AC disconnects are rated for AC and the DC disconnects are rated for DC. And then there's ground fault detection interruption. And mostly, GFDI, by the way, is different from GFCI, ground fault circuit protection, because the GFCI typically trips on 5 milliamps. You put one of those in a PV system, it's going to trip every day. So these trip at a higher current, and they're intended originally for fire and arc fault protection, as well as some protection of personnel. But there's arc fault detection also required for any PV system mounted on a building, and the arc fault detection is supposed to be your fire protection. All right. So again, all right, just note that there's a lot of information here that I don't feel a strong need to read to you, because you all can read, and this will be available. Most important thing is how the GFDI operates properly, and the idea that you just don't connect anything on purpose to ground, because that's the grounding. The grounded conductors are connected to the grounding conductors at only single point. You need single point grounding, and that is generally done through the GFDI device. So you don't ground the green wire to the white wire or whatever anywhere along this system. You let the GFDI device take care of that. And also, if you ground a conductor, in some cases, like with a 1,000-volt system, you might have some of them that have negative grounds and some that have positive grounds. With transformerless inverters, which most of them are now, and particularly this example, the array itself has to be ungrounded, but that's still covered in the inverter as far as the GFDI protection is concerned. Okay, component locations, modules, obviously they're exposed to the sun. Junction box has to have a UV rating and be weatherproof, at least a NEMA 3R, and oftentimes NEMA 4. And, outside components, outside use. Most inverters are listed for outside use if they are straight grid connect. The battery backup inverters generally are not listed for outside use, but we're not doing those in this particular session. Combiner boxes, of course, obviously need to be weatherproof. Grounding, if you're over 50 volts, you have to have all your components grounded, like your array metal, the array mount metal ones, the frames of the modules, and anything metallic has to be grounded with a grounding ground lugs. Okay. Need to specify bonding jumpers across array mount sections. The people who manufacture the arrays, they give you the sheet that tells you exactly how you have to bond from one section to another. And some of them, you snap them together and they take care of the bonding. You don't need any additional bonding jumpers. So look at the specs on the array mount to see whether you need any additional jumpers. Equipment grounding conductor 250.122 gives you that. Do we have a question here? What happened? No, I don't see any Q&As. The little box on top of my computer dropped down, and I want to see what happened. Okay, so the grounding electrode conductor, you may or may not need it. You might be able to use a grounding electrode conductor that's already a part of the system, especially if you're backfeeding a breaker in the main panel. Or if you are even, if you're backfeeding a conductor in the main panel, you can generally just tie your ground wire to the ground in the main panel, and it'll be grounded by the existing grounding electrode conductor. Even if you're doing a line side or load side tap outside, a tap connection, typically there's going to be ground wire in wherever you're tapping, and you can use the connection. On the other hand, if you put the array on the roof of garage and then feed it to a panel in the house, you'll probably need to drive a ground rod or two at the location of the garage and have a grounding electrode conductor there. So again, pay careful attention to 250.166. Oh, I see what I did there. I touched my, okay. So let's take a look at a 14 module microinverter. A 280 watt module has the output voltage at standard test conditions between 26.1 and 43.8. Output current, 9.2 amps max. Okay, that's the maximum power current. So you find a microinverter that has input voltage and currents that fit this range. And once you do that, you don't need to do any other calculations because this is just one module. You can do your, the thing is the microinverter is going to tell you what size module that you can use. And it will automatically meet the high and low temperature requirements. So you don't even need to do that calculation as long as you use the appropriate microinverter that fits with that particular module. Okay? And the output voltages on microinverters are usually 240, except sometimes they can be used on 208 as well. In fact, essentially always. For a 240 volt output, the current is going to be 1 amp, okay? And the idea is that, 240 times 1 is 240 watts. So that means that it acknowledges that this 280 watt module is highly unlikely to ever be running at 280 watts. All right. More than likely, it'll be at 240 or less. And as long as it's at 240 or less, this microinverter is fine. Your annual performance is going to be fine, no problem. And you find that out, the specification sheet on the microinverter is 2 pages long, as is on the module and almost every other piece of equipment, 2-page spec sheet that gives all the performance numbers. So 14 modules, 14 microinverters at 1 amp a piece, you get 14 amps at 240 volts. Microinverters themselves satisfy UL 1741. So therefore, if the utility goes down, the microinverters go down, and there's no more power leaving beyond the modules themselves because the microinverters are mounted directly underneath each module. All right, that's very nice because that doesn't add any additional cost to the system to satisfy rapid shutdown. Furthermore, the microinverters do maximum power point tracking on the module to which they are connected. So therefore, if you've got one module that's shaded and everyone else is not, or 2 modules are shaded, whatever, only those 2 modules are affected, the rest of the array works just fine. So a single 2-pole 20 amp circuit works fine here because a 15 amp isn't quite big enough. You need 125% of that 14 amps. And that 15 amp doesn't quite do it. So 2-pole 20 amp, and you're in, as long as there's room for an extra 2-pole breaker in the main distribution panel. If not, you do a tap with a 2-pole 20 amp circuit breaker in the or 2 volts, a couple of fuses if you want to use a fuse disconnect in order to get into the tap connection. Microinverters are smart grid ready. They're about 97% efficient, sometimes more. Some will support up to 330 watts. Some support even more than that. Now they got more stronger microinverters, but this is the one that would be picked for this particular system. And they've got factory wired cables that go from inverter to inverter. So you just snap them in, connect the connectors between modules, open wiring to a single junction box. These inverters, some can be on the east facing, some on the south facing, some can be on a west facing roof, because they're all connected in parallel. They are all current sources, so whatever current any one of them decides to add to the mix, it's just fine. No module affects the performance of any other module with this kind of a system, and that's why the current designers and installers love these things. And here's an example of 14 microinverters, all connected. Now I'd say in a series connection, but that would be a lie, because a single line diagram, there's actually a plus and a minus, or line 1, line 2, call it, that these inverters are actually being all connected in parallel here. So each one adds an extra amp to the line as they go down the line to that junction box. At the junction box, you got a maximum of 14 amps, 13 amps coming into that last inverter, 12 coming into the second to the left, and so on until you get to the first one, where there's only 1 amp going between the first inverter and the second inverter. And that system monitor, again, probably that's going to be included in the combiner panel that combines and has communications, and then a single circuit breaker going into the distribution panel. Adds a little bit of cost, but it also adds a whole lot of reliability and the ability to monitor. All right, so how do you estimate the performance of these systems? We're going to make it, folks. We got 9 minutes, we got 10 minutes. National Renewable Energy Lab System Advisory Model. You can Google NREL SAM and you can download it. All right, you just need to give them your email address or something, because they have to show how many people are using the program to justify that they're able to make it available. Select where you're located, select array size, the azimuth, the tilt. Put in information on the equipment if you have it, and run the simulation. You know, go off, get your coffee. The problem is the simulation comes back in less than 1 second, and you can plot the results. So here's the typical input screens here. And you see that it gives the efficiency of the inverter in that one in the bottom middle, and that you can see a module performance curve if you've actually told the system what kind of module you're going to use. And you got the location information in the upper left. Okay. And then we talk about the array. What's going to happen with the array? What's the tilt? What direction is it facing? Is it shaded or not? And then you run the simulation, and here's your month-by-month performance estimate of that particular system. And you notice that May, June, July, and less in June, interestingly enough. So it must be raining more in June. And in May and July, not quite as rainy, and kind of what you'd expect. December, usually a system's probably not going to put out as much, as a little sun's at more of an angle, and it's tilted a little. And here's a question. Let's take a look at that. Let's see, my home has a main roof and a lower roof. When we had the lower roof replaced 2 years ago, the roofer said that solar panel. All right, well, it's an issue of shading. And you can tell that by looking at your roof from a Google Earth. Just if you've got Google Earth on your computer, put in your address and zoom in on your roof, and it'll give you some idea of whether it's shaded or not. Now, the other thing here is that shading isn't as big of an issue anymore now, because the modules are so cheap. And the systems are so cheap. So even on a lower roof, and I've seen a number of lower roofs now in the last couple of weeks, where they're putting modules, even north-facing roofs. And again, because even though you're maybe not making 6 cent kilowatt hour electricity on these roofs, you might very well be making 12 cent per kilowatt hour electricity, which is still probably cheaper than the electric rate, certainly if you're in New York or most parts of New England. So Carol, chances are, I mean, 10 years ago, the roofer or the answer you got would have been exactly the right answer because things were a lot more expensive then. But if we're talking cost effectiveness and the performance and all, your lower roof might be a good candidate at this point. And if you can talk to a solar dealer, they've got all the software that'll do that analysis for you. And they'll even give you a cost effectiveness answer. And your roofer wasn't necessarily wrong, maybe just a little bit outdated. Okay? So there is a good chance that, let's see, what do we got? Do I see any reasons why not to install on a side roof facing east in the northeast? No, I don't see any reasons for not doing that. And what you do is you do the simulation and see what it looks like in terms of the cost effectiveness of putting there. And if it looks like your overall system is still making electricity that has a life cycle value of less than what you're paying for electricity right now, you put them almost any place they'll fit. I was very surprised because I hadn't seen these analysis recently. I'm about 2 years behind up until 2 weeks ago, and big change. And that's why it's important to understand this stuff, because the changes are going so fast that what may have been true 2 years ago may now no longer be true, that you maybe can do it even though it wasn't advisable 2 years ago. And Carol, I hope that's a good enough answer. Okay, would standby diesel engine generator affect PV system when utilities offline requiring control interface to shut down PV inverters? Actually, you need to be a little careful with that. What you don't want is your PV system trying to deliver power to the standby diesel engine, because then it'll try to run it backwards. So it depends on how big your diesel engine. That's a pretty big generator with diesel. When utilities offline, you would, if you have already an existing diesel backup, you would probably just shut off your utility disconnect, your PV disconnect. If you have a straight grid connect. If you've got a system with storage, then that diesel generator can be an alternate source in case your storage runs low. So it's with storage and additional fossil backup, you can minimize the amount of fuel you're going to burn. One thing about any kind of fossil generator is that if they run, let's say you got a 5 kW fossil fuel generator and your load on it is only 200 watts, the efficiency of that is really, really, really small. And you're making something like $1 to $1.50 per kilowatt hour electricity doing that. So you really don't want to do that. If you have a gasoline generator, you would like to run it at 80 to 90% of its rated output. And if you have batteries in that you can store that output in, then you don't need to run it nearly as long. The batteries make the system a whole lot more efficient, and you don't have to breathe that smelly diesel fuel or even natural gas that gets pretty smelly if you have a really big generator. All right, so that's my comment on that. Okay, we're almost done here. Let's just finish off, and then we'll keep it open for questions until it's time to go for lunch. Okay. You notice here, this LCOE is levelized cost of electricity. So in this particular simulation, we're looking at 9.49 cents per kilowatt hour. And that was because the system was a lot more expensive. If I'd run this same thing yesterday, it would have probably come out at about 6 cents a kilowatt hour. So this is a simulation on NREL-SAM that gives you the economic analysis as well in terms of levelized cost of energy. What that is the amount you'd have to sell your electricity for over the life of the system in order to pay for the cost of the system itself. So if you can get more than 9.4 cents, and of course, if you're replacing 15-cent electricity, then you're looking at 5.5 cents a kilowatt hour profit on every kilowatt hour you generate, plus paying off the system beyond that profit. Okay, where are we here? Well, that's the end. Young man on the right is now studying electrical engineering in Minneapolis, St. Paul, and his baby sister just gave birth to my great-grandson. So thank you for being here today. And believe me, these kids will appreciate it. We got to install PV like there's no tomorrow, or there won't be a tomorrow. Okay, so let's now see if there are any more comments or questions. Let's see, check on the time. We're at 12:01. So any other questions or comments? Now's the time, quickly. Otherwise, be sure to check the chat box because there will be further instructions for what to do next in terms of if you have to take a quiz or downloading certificates and things like that. Okay, thank you, Carol, and I hope you get some PV on that lower roof and then it'll pay for itself. Okay. I don't see, okay, there's something, okay, now in the chat, you got all the instructions there about the quiz link, certificates, all that stuff. So the next thing you do before you stop is go to the chat box for further instructions. And thanks to everyone, happy holidays, whatever might apply. Glad you were here today. I hope it was worth your while. And hope to see you again at some future webinar, maybe the one on photovoltaic systems with battery backup. If you like this one, if you feel it's something you want to get more into, the backup system is a good follow-up. Okay, I'm going to stop sharing that black screen. We are back to the main screen. We still have 19 participants signed in. You notice that on the main screen, to get out in the bottom right-hand corner, you click on leave. Oh, here's a question. Let's see what we can do with that. Oh, okay, got that one already. Okay, there's a chat announcement from the host. 15 participants left. I generally don't sign out until pretty much everyone has signed out in case something else comes up. Another chat, here's a Q&A. For the quiz, look at the chat box. That tells you where the quiz is. Okay.